What's poppin', dogs? Mr. Allen here with some graphing of cubic polynomials, and these two are already in factored form. And that is ideal when it comes to finding your x-intercepts, because I can just set those factors equal to 0 and solve. And then we'll get our y-intercept. So first off, 2x plus 5. Don't just think it's the opposite of whatever this number is. Yes, that is true with these two here, but 2x minus 5, if I set that equal to 0, 2x plus 5, equal to 0, I'm going to subtract 5 first, and then I'll have 2x equals negative 5. Then I have to divide by 2. So I get x equals negative 5 over 2, or perhaps you prefer seeing negative 2.5. That might be easier to spot as an x-intercept here on the graph. But we'll put it in fraction form for our ordered pair. So let's write down x-intercept, or x-intercepts. It's going to be negative 5 over 2. Comma 0. Make sure anytime you're writing an intercept that you have that comma 0, right? It's an ordered pair for x-intercepts and for y-intercepts, so you got to have an ordered pair there. It's whatever the number is, comma 0 for x-intercepts, and it's 0 comma something for your y-intercept. More on that later, though. All right, other x-intercepts. I've got x minus 3 equal to 0. Well, that's going to give me positive 3 comma 0. And then x minus 5 equal to 0, I'd add 5 to both sides. So I'm going to get 5 comma 0. And if you didn't quite follow that, I'll do a little more side math over here. I could say x minus 3 equals 0. I'm going to add 3 to both sides. And now I get x equals positive 3. That's how I'm getting that, okay? But again, I stress to you guys, don't just think, oh, it's just the opposite sign, because that will get you screwed up on that one right there, right? Be very, very careful. Okay. So we've got our other two x-intercepts. We got 3, 0, and then 5, 0. Woo, almost ran out of room. Now you'll notice my y-axis here. My y-axis is not scaled. And that's on purpose. Because with a lot of these problems, the y-intercept can become very, very large. There's graphs where like it's 120, 0, 120 is your y-intercept. Well, we're not going to mark that all out or expect you to scale it. So we leave it unscaled. We'll plot our y-intercept wherever it is and then label it. Okay, so for my y-intercept, let's see here. If I plug in 0 for x, right, that's how I get my y-intercept. Plug in 0 for x. So let's do that. I'll actually do that in a slightly different color so we can make it pop a little more, right? If I plug in 0 here, I'd have 5 for that factor. Actually, I'll do it right underneath it. So we get 5 times, if I plug in 0 here, I'd get negative 3, right? Because 2 times 0 is 0, plus 5 is 5. 0 minus 3 is negative 3. And then 0 minus 5 is negative 5. So now I just need to multiply those three together. Well, let's see here. I like 5 times negative 5. That's a negative 25. Times negative 3 would be positive 75. So 0, comma, positive 75, that is my y-intercept. Okay. So as you can see, that does get kind of out of hand there. You could put it anywhere on here. I mean, I could go really low if I wanted it, and I'll just label it. But I'm thinking, 75 is kind of a large number. Let's go ahead and label it as such, and I will put it something like this. Let's see here. I'll go 0, comma 75. Okay. There we are. 0, comma 75. That's my y-intercept. I don't have to label these because it is scaled out. And now we're just going to go ahead and draw on the graph. There is a little bit of planning, okay? We want to think about, like, well, what does our graph look like? Well, this is a positive cubic function, so it's going to look something like this, okay? And do I have any weird features on this graph, like zeros with a multiplicity of 2 where it bounces or anything like that? No, these are all 3 different x-intercepts, so the x-axis is just going to be right through like that. Just bing, 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 bing. Okay. Where's my y-intercept going? My y-intercept is between these two right here. And is that an absolute, like, is it a maximum or a local maximum, excuse me? Is this the highest point necessarily? We could use a calculator to figure that out. We could do a table of values, a lot of guessing and checking. This one is pretty close to right in the middle, but this one is a little bit further away. So I'm thinking I would come up, I'd pass through it a little bit, and then come back down. So I'm thinking my high point is somewhere maybe right up in here. All right, so I'm going to be over on this side with my y-axis. So I'm going to pass through, come back down, okay? And it's good to have a bit of a game plan when you are about to graph these things so that you don't end up with like a really wonky looking graph, all right? So I'm going to be coming up here. I'm going to pass through it just a little bit, come back down, and back up. And honestly, that's not my best effort when it comes to cubic functions. It can be kind of tricky, especially when you have to come up really high. But overall, not half bad. I'm going to re-plot this guy right here. My main point here is that this is not the high point, right? I'm thinking that it has to pass through a little bit more and then it comes back down. We could check a graphing calculator and be sure about that. But usually in this stage, your teachers are just wanting you to get these 3 points here, your x-intercepts, your y-intercept, and perhaps an additional point, but usually that it will suffice in this scenario here. All right, so there we go. A lovely cubic function. Note that we have arrows on both ends here. Note that it does not flare out at the end or over this way. It doesn't come back this way. It doesn't ever get vertical because it has to pass the vertical line test, right? This graph cannot pass through a vertical line more than once, otherwise it's not a function. And it is a function, so we got to make sure that the graph looks like a function, okay? Always a little tricky, especially at first. Like, there's some bad graphs out there. I wasn't good at them either, right? I was not good at graphing in general until I practiced a lot. So it does take a bit of practice. All right, this next one over here, you guys. I'm gonna go with we'll go with blue. We'll go with blue for our x-intercepts here. So my x-intercepts. Let's see if this one's they're not too bad, right? I got looks like -1, 0. If I set that equal to 0 and solve -1, 0. Over here I've got 4, 0. And you may be like, whoa, bro, whoa, what's that 3? Why'd you skip over that 3? Why did I? Why did I skip over that 3? Well, that's a lead coefficient. There is no x that's attached to that 3. Therefore, it does not give us an x-intercept. It'll actually, if you think back to quadratics, a lead coefficient out there is a vertical stretch or compression. In this case, it's a stretch because that value is greater than 1. So it's going to get vertical faster. It's going to get higher up, and that will happen. It'll impact my y-intercept, but it will not impact any of my x-intercepts. So don't worry about that 3. The math going to work out how the math works out, okay? Now, next thing here, I've got, oh, wait, don't I already have this one? -1, 0? I do. So I'm just going to write here multiplicity of 2 for that one, okay? Sometimes we'll say, how many unique x-intercepts does this function have? This says 2 unique, but it's a total of 3, technically. But 2 of them are unique. 1 of them repeats, right? So that multiplicity of 2 is going to have a special graphical look to it. It is going to bounce off of your x-axis, right? Either from below, bounce back down, or from above, bounce back up. It's tangent to the x-axis, okay? So the multiplicity of 2 does look different. These all pass through. This one will bounce, all right? Next up, my y-intercept. If I plug in 0 for everything, what are we going to get? Well, when I plug in 0, again, I'll do this like right below it so we can see the work. If I plug in 0, I've got the 3 out front. That's going to be 1. That's going to be -4. And that'll be 1. So I've got 3 times 1 times -4 times 1. Well, the 1s don't matter, so it's really just 3 times -4, which is -12. So I plugged in 0, I get -12 out. That's how I get my y-intercept. If you want a y-intercept, you plug in 0 for x. That will work for any function that you ever encounter if it has a y-intercept. Not every function has a y-intercept, okay? Not every function has an x-intercept. But if it were to have a y-intercept, plugging in 0 and evaluating would get the job done, okay? So let's plot all of these because I kind of just did everything and didn't plot it. I've got -1, 0. I have 4, 0, 1, 2, 3, 4. And we have 0, -12. I'll just put that right here. And I will do the ordered pair like so. 0, -12. Beautiful. All right. Now, I got to figure out how I'm going to connect the dots here. Well, this is a positive cubic function, so it is going to look like this one, but I'll do the rough sketch over here because there is something a little different on this one. Whoops, there we go. I'm going to be bouncing, right? I'm going to be bouncing off of the x-axis. And where am I bouncing? Am I bouncing at the -1 or the 4? Well, the -1, 0 is the one with the multiplicity of 2, so I'll be bouncing there. Now, the only places I can bounce on a graph like this would be at a local maximum or a local minimum. Notice that I did not say absolute maximum or absolute minimum because there is no absolute max or min in a cubic function. They just keep going, right? But locally, I could have a max right up here. Locally, I could have a minimum right down here, but there's no absolute. So if I'm only able to bounce off of these 2 points and it's the first one I need to bounce off of, I will bounce off of the local max here because that's the first one. Which means my x-axis will look something like that. It'll be passing back through on this one. Where is my y-axis going to be? Is it going to be to the left of my local minimum or to the right of my local minimum? And that can be really difficult to figure out. Well, since this x-intercept is so far over here, I'm thinking if I bounce off this one, I'm going to need to pass through it to come back up in a nice curved way, right? That doesn't look all distorted. Because if I came up like this, and then I would have to like, woo, hurry on over there. That's not how the graph's going to look, okay? It's going to have some symmetry to it, or not really symmetry, but like, it's not going to look weird. Okay. I don't know how else to describe it. But that's what we're going to be looking like. I need to pass through my y-axis and continue down a little bit and then back up. So let's go ahead and try and do that in a wonderful, beautiful, graphical way. I'm passing through. And then I'm eyeing up like, okay, where am I about the middle? And I'll come back up. So I'm thinking like, whoop, boom. Right? You don't want to go too far and have to like come back because then it doesn't pass the vertical line test. Hopefully I didn't run off the graph there. I think we're okay. That looks beautiful. Oh my goodness. Got a little screen on my watch. There we go. So I've got my y-intercept, my two x-intercepts. Good to go. Don't forget to label that y-intercept. You can't just put the point there and call it a day. If it's not scaled out, like you could scale out 12 or you could just label it. At least that's how I roll with these types of problems in my classes, and I'd imagine most other teachers would probably do something roughly the same because nobody wants to mark that out 75 times, or, I mean, you could go by tens and put it in the middle, so no. Label it. That's about it. All right, you guys. Hopefully that helps, and I love graphing polynomials. They're kind of fun, right? Especially if they're in factored form, makes it super easy to find those key points. If you guys have any questions, pop it in the comments or find me in the halls if you go to school where I teach. Otherwise, thanks for watching.